Good morning, everybody. Thanks so much for joining this Expanse dedication. We're thrilled to have you here. My name's Sean Strandy. I'm the Deputy Director at SDSC. We'd like to kick this off with a brief video to give you some highlights of the Expanse system, and then I'll roll into introducing the panelists for today's meeting, and we'll follow that with some Q&A from y'all. So thanks again for joining. See here, let's get the tech rolling. Let's see, all right. Let's go full screen here.
Hi, I'm Sean Strandy. I'm the Deputy Director at the San Diego Supercomputer Center. The interesting thing about the systems we operate at SDSC are they're focused on what we call the long tail of computing. Most of HPC is composed of lots of people running relatively small and modest-sized computing jobs. That puts a lot of pressure on the system to deliver to that very mixed workload. And then, of course, the biggest overall impact and metric for us is science. What cool science has been done? How have we advanced discovery? Here with Expanse, of course, we've announced a couple other things. Direct integration with commercial cloud. Those same users, whether they come in through a typical batch job or a science gateway, could actually have that job run in the cloud instead of on-premises with Expanse. Some interesting aspects of Expanse are we came up with, partnering with our friends at Dell, a scalable unit concept. So Expanse is composed of identical scalable units. Each one of those scalable units accommodates a huge fraction of the community's workload. And sort of the sum total of it is a really powerful system with an incredible amount of compute potential in it for a lot of users. We anticipate we'll be serving 50,000 or more users with Expanse. The thing that's most gratifying at the end of the day, we're putting systems on the floor and we're running them on behalf of the community. And the whole team at SDSC and our partners at Dell and AMD and in the project share that sort of same idea that, it's what we're doing is important through the whole pipeline of scientific research. The AMD Rome processor, we're deploying a 64 core count version of that, the 2.25 gigahertz processor, 128 cores per node, 93,000 cores in the system provides a huge amount of computational throughput for our community. So that's really, really important. AMD's been moving ahead with their PCI Gen 4 work, their innovative Infinity Fabric, and the Zen 2 core technology and the chiplet technology in the Rome processor is forward-looking. The fact that Dell has been working closely with AMD on the server design to incorporate the AMD processor. And so our tagline with Expanse is computing without boundaries.
All right, well, that's enough of that guy. Let me now bring up our panel introductions here. And we'll get going with some presentations to give you a more in-depth look at Expanse. So today we have with us Dr. Mike Norman, who's the director of the San Diego Supercomputer Center and the PI of the Expanse project. Christopher Irving, who's the manager of the HPC Systems Group. It's his group that really got the system up and installed and running. Hello, Christopher.
Morning.
Great to be here. Mahidar Tataneni, Dr. Tataneni is the manager of the User Services Group. Mahidar, are you there?
Yep. Hello.
Great. There we go. Mahidar's team is really responsible for getting the applications and the environment up to make the system productive. So we're looking forward to hearing from him today. And finally, Dr. Bob Sinkovitz, who's the Director of Scientific Applications. Bob, you there?
Oh, hey, hello, everybody.
Great, Bob. We're looking forward to hearing from you. I'll be your moderator today, and just a reminder, we have a Q&A section. Please feel free to drop questions in there. We'll pick them up as we go along in the conversation. So without any further ado, I'm going to stop sharing here and welcome Dr. Mike Norman, the the brains behind this endeavor here to tell us about Expanse and how it's going to help change the world.
Great. Good morning, everybody. It's really a pleasure to be here. I had not seen that video before, and it really does a great job explaining a little bit why we call the system Expanse and what we mean by computing without boundaries. And so I'm going to reiterate on a few of those points just so that we all understand where we're coming from and where we're going. All right, trying to go full screen there. Great. So I am the principal investigator for the project, but I'm also a user of Expanse. And I got to tell you, it's a great system, super fast, very flexible. So here's the status report. We installed the hardware and software in July and August. In September, we conducted acceptance and reliability tests. In October, we let on early users, about 30 teams. And in November, just a week or so ago, we had a very successful NSF site review. And so any day now, we will be pushing this machine into production. So what's new and cool? Isn't this just yet another HPC cluster? Well, at one level it is, but there's a lot of cool new things about it and what you can do with it. As Sean mentioned in the video, there's over 93,000 AMD Zen 2 cores packed into 128 core nodes. That's a lot of cores on a node. That's something that I certainly haven't seen before. 208 NVIDIA V100 GPUs that are just wicked fast. We are integrated with the cloud, as I'll mention in a bit. We are integrated with the Open Science Grid. We have an interactive notebook capability, which you can access through the Open On-Demand portal. We have science gateways galore. And here's something really new and cool, which is that we can operate both Slurm and Kubernetes partitions simultaneously on the system, and that those partitions can be resized. We have a Ceph object store in addition to our Lustre file system, and the object store is really for data sharing. It also assists with the composable systems applications. And then finally, what's new and cool, this computer is actually cool. We have direct liquid cooling on the system, which is a first for us at SDSC. So this is the project on one postcard, if you will. It is a 5 petaflop system for both HPC and data intensive computing. The uniqueness, I would say, has to do with the remote cyber infrastructure integration with the cloud, with distributed heterogeneous resources and the Open Science Grid. But the operations, the way we run this system is also quite innovative. We will support composable systems, high throughput computing. Science gateways is something that we've been doing for a long time. Interactive computing is coming to the fore on Expanse in a way that we have not done before. Containerized computing and cloud integration. As the video said, the system itself is made of 13 scalable units, 13 racks, each identical, which contain 56 CPU nodes and 52 GPU nodes. I said that wrong. It's 52. Never mind. Christopher will explain it. But so the point is, it is a scalable architecture in the sense that you can just add more racks, and the jobs are fully connected within a rack, which allow the nodes are fully connected within a rack, which gives you excellent scaling. within a rack. And one rack contains 7,128 cores. So it's quite a parallel computer in its own right. So the next 3 slides just touch a little bit on this integration with remote CI. This is really what we're pushing on this system. So this slide explains a little bit about the cloud integration approach. This has been pioneered through the Cypress Gateway, which is this very large community gateway for phylogenetics. A user submits to the gateway and previously would run jobs locally on the computer, in this case Expanse, but based on just a setting in the scheduler, the user can opt to route those jobs to AWS. And so AWS is up here. We connect to that through Internet to Cloud Connect. And down here is a piece of software that we have developed utilizing some open source software from HashiCorp called a scaler that is able to provision the requested instance in the cloud. And meanwhile, the data is migrated from the home file system on the gateway directly to AWS. So that has been demonstrated and been in production for a number of years on Comet, and we're moving that over to Expanse, and we will be entertaining applications from others who would like to do the same. Now, bear in mind that you have to bring your own money if you want to compute in the cloud. We do not have a budget for cloud credits, and so this is a capability that eases the use of the cloud, but does not pay for it, just to be clear about that. The second integration I want to talk about is the composable systems capability. This is intended to support complex distributed workflows, and I'll give you an example in the next slide. And so here you see what the Bright Cluster Manager can do. It can take the physical cluster and divide it up into a Slurm partition and a Kubernetes partition. The software itself is called CM Scale. And this can dynamically provision these portions. Now, the kinds of applications that can be done this way are exemplified by the Wi-Fi project, which is done out of SDSC. This is a wildfire management cyber infrastructure that takes in a variety of remote information sources, real-time sensors on towers, weather data or weather simulations, fire perimeter from aerial vehicles, information about the land topology and vegetation cover and so forth, and integrates it all together into a system that is able to make predictions in near real time on the spread of the fire. And so when we say that we are offering composable systems to the community, what we're really saying is that we are making available the team of experts that did this. Now, if you have an application that looks like this, it doesn't have to be this complicated, you can access that expertise through Exceed. So that's pretty cool. And then the final integration is with the Open Science Grid. This slide, if anything looks like an integration slide, it's this slide. Fortunately, we have Marty Candace, who created this slide, available for the Q&A, but I would just ask you to look at colors. The purple is a virtual organization, which is what a project is called within the Open Science Grid. They have a software installed on their end. They talk to the open science grid, which operates this glide-in factory. And then over here in red is the Expanse cluster. And while a lot of this is standard, what is new and what we have accomplished is that if you consider now that one node of Expanse has 128 cores, and that we can do shared usage of nodes, meaning we could run 128 simultaneous single core jobs on those nodes. What we've done is a particularly good integration on the accounting side of things, such that individual users in a virtual organization can be accounted for as their jobs are placed and executed on Expanse. And so it's not just, here's a here's an execution target. Here's an execution target that knows who's coming in and what they're using, because accounting is, of course, very important for everybody. So our user support team, led by Mahidar Tatneni, will help you use this wonderful system. We are a Exceed Level 1 resource. There is an overlap of 4 months between Comet and Expanse operations, allowing for transition. We are standing up a new program that we call HPC at MSI, where I can make discretionary allocations to minority serving institutions in order to onboard their researchers and educators. And then finally, the advanced support required to do the cloud bursting, the composable systems, is available from SDSC staff on request through a proposal. So that is what I had to say, and I would like to just finish with this logo cloud of our collaborators and our partners, Dell, AMD, NVIDIA, Intel, Eon Computing for the storage, Open Science Grid, and Mellanox for the networking. And here in the lower left, you see some of the team members. So thank you very much.
Thank you, Mike. I'll just mention, again, we have a Q&A box there in the lower right for any questions that come in. Our team is answering those kind of in real time. I'll just, one person asked a question about why would you integrate with the cloud, and multiple reasons. One, there may be resources in the cloud that Expanse doesn't have, and we can help access those by working with you and developing that capability. There may be data sets in the cloud that people want to work on. So it extends the boundary of Expanse and offers capabilities that the system itself may not. It's obviously got capacity. So, if a team comes to us with a proposal for a cloud application and the funding that they have to do that, we can work with them to support that kind of a workflow. So it's something we see coming, and we're prepared to address that. So again, please feel free to get your questions into the chat here, and we'll get to those as we go through it. So at this point, I'd like to bring on Christopher Irving, who I mentioned at the top of the session here, is the manager of our HPC Systems Group. Let me bring up the slides here. And again, Christopher's team is really the group that was there on the ground getting all this done. And lest anybody forget, the entire deployment of Expanse was done in the context of COVID-19, and literally a purchase order, from the point of executing a purchase order to getting the system up and running under extenuating circumstances and with constraints imposed upon us by the university, the state of California, and so forth. His team really just did a masterful job in getting the system up. And so it's really my great pleasure to hand this over to Christopher for his presentation. So thank you, Christopher.
Sure. Morning. So this morning I'm going to talk a little bit about the Expanse hardware architecture. You've heard a little bit about it already from Mike in the video, and so I'll just go a little more detail about some things. So next slide. So a lot of this has already been mentioned, but Expanse is made up of 13 scalable units, what we call SDSC scalable units. So total of 728 standard compute nodes. A lot of this, I think, has already been mentioned. There's a 12 petabyte Lustre file system. We will have a 7 petabyte Ceph file system later, coming actually in April. As in addition to also some 52 four-way GPU nodes. Go ahead and go to the next slide. I'll talk more in depth about each SSCU. So the SSCU is really our building block of Expanse, and within each one of these SSCUs we have 56 compute nodes. These are Dell C6525 chassis. So and each node has 2 AMD EPYC processors with 100 each with 64 cores, so 128 cores total, 256 gigabytes of RAM total, and each node has node local scratch, which is made up of 1 terabyte NVMe drive. Also within the rack are the four. Each rack has 4 GPU nodes. Each GPU node has 4 NVIDIA V100s. With NVLink as their interconnect, so no going over the PCI bus for communication between the two. Each one of these has a 1.6 terabyte NVMe drive as its node local scratch. A couple other things, as has been mentioned within the features of the SSCU, is the direct liquid cooling for the CPU nodes, the regular standard compute nodes. Also, each rack has a HDR switch and a Ethernet switch as well, and I'll talk about that next. You can go ahead and go to the next slide. So Expanse actually has two network fabrics. It has an HDR two-level fat tree, and it also has an Ethernet fat tree as well. So within each rack, as I mentioned, there's an HDR switch with that gives full bisection bandwidth within the rack, and from there, the switch connects back to our 5 spine switches. There's two HDR 200 gigabit links per rack back to the spine switch, each spine switch. So, and then there's 100 gigabit per second down to each node. So that gives us 3.1 oversubscription between racks into the core. But within, as I mentioned before, within each rack, there is full bisection bandwidth. On the Ethernet side, we have our core is 2 100 gigabit Ethernet switches in a MLAG virtual chassis, and then within each top of rack switch within the SSCU has a 100 gigabit connection back to each one of those core switches. So they have 200 gigabit connection total back, and then our connection to our data center is actually a 400 gigabit connection to our data center core racks. You can go ahead and go to the next slide. So our Lustre file system, we've kind of designed our Lustre file system very much in mind with the idea of trying to address some of the issues we've seen in the past. One of those salient issues is is small I/O. So we have a 12 petabyte Lustre file system. It uses all NVMe based metadata servers, and so we have 4 of those in HA pairs. So even if one of them fails, another one can take over for it within the pair. In addition to that, we have our standard 18 OSSs that uses SATA drives. So our total file capacity, we were estimating it to be around 3 billion files. Performance-wise, it can do 140 gigabytes per second file system bandwidth and over 200,000 IOPS. It's actually a low water on that. Some of the features that we're taking advantage of Lustre in order to address these issues before is D&E phase 2, striped across all 4 of the MDTs, and data on metadata for small file performance, so that files of a certain size will land on the metadata servers, on those NVMe drives, and take advantage of that low latency NVMe and not having to go out to the OSSs in order to write the data. So that helps us with issues that we've seen in the past with small I/O. And with that, I think I tried to cover it pretty quickly.
Christopher, thank you. One of the questions came in, which has been answered through the Q&A, but I thought the general audience might be interested in knowing kind of what's the design expandability. Can it be expanded, and to what extent can it be expanded in its current form?
We're talking about Expanse in general?
Yeah, the number of scalable units, can that be?
Yeah, so that can be increased, and really it just depends on, the way it's designed right now, we can easily add 4 or 5 more scalable units. And if we really wanted to go beyond that, it wouldn't be hard. It would just be, maybe a small redesign in probably our IB architecture or IB fabric.
Great. There was another question too. I'm sure folks are very intrigued by this Slurm and Kubernetes capability, and I know you yourself are just getting familiar with it. But can you maybe just talk about how you see that working and kind of where you are in understanding that functionality?
Sure. So this would be something that some people would have to come to us with a project and work with our advanced user support on setting up. But we do have the capabilities of basically taking nodes, basically moving nodes back and forth between the 2 different workload managers. We have Slurm workload manager, and we have Kubernetes, and then basically what it counts as a meta scheduler that will look at those and could potentially move nodes dynamically from under one workload manager to the other, and then allow for people to run jobs or run tasks as under Kubernetes as opposed to Slurm.
And this is a capability you're using in Bright.
Yeah, so we take advantage. Yeah, the metadata scheduler and other features of Bright are used to provide that.
Great. Thanks so much, Christopher. Again, reminder: use the Q&A if you have additional questions here. Okay, with that, I'm going to move to our next presenter, Maidar Tatanetti, who, as Mike mentioned, manages our user services group. And so Christopher's group hands him some functioning hardware with a system on it, and then somewhere in between that and the users, some magic has to happen, and that's what our user services team does, and they're quite good at that. So Maidar, tell us what you've learned about Expanse and how this can be used for science research.
Sure. Yeah. Thanks. Good morning, everyone. This is Mahidar. So I'll talk about some Expanse application performance testing that we did, and also the software stack itself. So on the next slide, I can start with the overview of what we did. So once we got handed the system, the benchmarking environment and the software stack on Expanse is essentially installed using SPAC. And we were able to leverage a lot of the existing development that's already been done in the community, for SPAC community, to kind of install packages. And in addition to that, AMD is actually working to push in their performant versions of their applications into the SPAC framework. So in the long term, that's a good way to install packages on the AMD-based system. So some of the benchmarks we chose were typical of what runs on Comet and what we expect will run on Expanse. So it's a range of applications like in molecular dynamics, neuroscience, CFD, quantum chemistry, bioinformatics, and weather code. So you can see that in the application list there, the GROMACS, NAMD, Neuron, OpenFOAM, Quantum Espresso, XML, and WRF. One thing that we did find running on these systems, and I will talk about this a little bit on the next slide, is you have to be cognizant of the NUMA architecture of the node if you want to get good performance, and that actually led us to develop Affinity scripts for hybrid codes so that we align OpenMP tasks with the L3 cache, for example, so that you have all the threads on the shared L3. And so this is something that we developed while we were benchmarking, but obviously it's going to be available to users when the machine's in production. The other thing we looked at is the AMD math libraries, AOCL libraries, basically. They're used in some of the benchmarks that we did, like Quantum Espresso and NAMD, specifically for the FFTWs, I think. But this is something that has given us good performance, and it was borne out in early user testing with some users getting the best performance with the AOCL libraries. So that's another thing we tested out initially. Now, in terms of what we get for performance, the speedups were anywhere between 1 and 2x per core basis on Comet. Now, remember that we have a lot more cores per node, so on a per node basis, this is easily over 5x. And most of the codes were in the 1.3 to 1.4x range in terms of a per core basis improvement over Comet. So overall, since we have almost 2x the cores and we are seeing these speedups, we should easily be more than 2x in terms of throughput compared to our previous system. So that will really help our long tail users get through a lot more jobs. And then on the GPU side, we have the V100 GPUs, and the benchmark applications again kind of represent what runs on the system. Amber and NAMD are quite commonly used, and so is GROMACS. And on the bioinformatics side, the Beast code is quite commonly used by the Cypress Gateway, so that's one we tested. In addition to that, we have a lot of the machine learning frameworks that we tested, like MXNet, PyTorch, and TensorFlow. Here, basically the speedups are between 1.3 and 1.9x, depending on the code, over the Comet P100 nodes. Again, most codes are above 1.5x in terms of per GPU basis speedup. So let me go into the architecture of the CPU on the next slide, and then we can take a quick look at some results. So the key on the CPU side is to understand the AMD EPYC architecture. This is really essential to get optimal performance. So the chip is, so what you see on the right top figure is essentially the one socket, one of the AMD EPYC chips. So it has 8 core complex dies, and in each core complex die there are 2 4-core CCXs. And on the CCX, you kind of share the L3 cache. And it has 16 megabytes of shared L3 cache. So overall, on the whole chip, you have 256 megabytes of L3 cache, which is nice. So you have these CCDs are connected to the memory I/O through the I/O die that's in the middle, and that's a 14 nanometer technology. So you have the chips, the chiplets at the 7 nanometer, and then the I/O die at 14 nanometer. And you have DDR4 memory at 3200 megahertz. It's 8 memory channels per socket, so that's double of what we have on Comet. And you see that in some applications where you get a lot of performance if you're tied to the memory bandwidth. Now, in terms of how this is abstracted out, on most HPC clusters, the configuration we'll use, and this is what we use on Expanse, is 4 NUMA domains per socket, which is the NPS 4 configuration. So what happens here is basically 2 of the memory channels and 1 quadrant of the chip is basically abstracted into a NUMA domain. So when you're running HPC codes, you have to be very aware of your layout and the new architecture that's being presented. So that's shown here basically in the figure on the bottom left, bottom right, sorry. So let's look at what we got out of this on a couple of codes in the next slide. So I picked out a couple of codes out of the list that was there before. Basically, the Quantum Espresso, this was one where we used AOCL libraries, and we got the best performance using the AOCL libraries. So the speed up over Comet on a per core basis, you can see is 1.38 at the low end and almost 1.6 on the high end on a per core basis. Now at the 768 cores, you have a 1.5x speed up on a per core basis. If you convert that to a per node basis, you'll see over 7x essentially. This is important because a lot of our users don't really run at very large scales. So the medium scale core counts, you're seeing such a huge increase in speed up. It should be very useful for people who are running at that scale. And on the right, we have a neuroscience code. Again, this was actually built with Intel compilers with the AVX2 architecture flag, and that's good enough to get you really nice performance. And you can see it's almost 2x faster than Comet on a per core basis at the high core counts. So that was just a couple of codes. I mean, we went through a lot of testing, and I think overall, as I mentioned, speedups were anywhere between 1 to 2x on a per core basis. Most of the codes being between 1.4 and 1.3 and 1.4x. So next slide, please. So on the GPU nodes, we tested a lot of codes, as I mentioned, and here I'm just showing you Amber, which is very commonly used on Comet, and this is a factor 9 benchmark with 91,000 atoms. And this was straight up SPAC-based install, and everything worked out of the box, and we got almost a 1.8x speed up over Comet on a per GPU basis. This is comparing to the P100 GPUs on the Comet side. And on the right, you see the Beast code comparison, and this is with the 104 taxa and 131,706 DNA characters. And this is quite commonly used on the Cypress gateway. And again, we saw basically between 1.4 and 1.45x speed up on a per GPU basis. So overall, one thing I should note is that a lot of these benchmarks were very steady across the system, and that's a testament to, I think, the liquid cooling and keeping all the parameters kind of steady. So we got really good in terms of stability, in terms of performance, with very little variance that was tied to either the CPU or the GPU side. So that's a quick summary of what we got out of application testing. And I think Bob's going to talk about some of the science results that were obtained in the early user period.
Thank you, Maidar. It's my pleasure now to introduce Dr. Bob Sinkovitz, who is the director of SDSC Scientific Applications Group. And so continuing this, my comment about from hardware to Maidar's team to Bob. So, you know, we get users on the system and then they would like to understand how to make the best use of the hardware and so forth. And so Bob and his team are instrumental in doing code optimization. That can be anything from making the best use of an architecture they're already using to moving to another one. And ultimately, you know, Bob's at the front line of really picking up the impact of the research that folks are doing. And so you'll see now with some of Bob's discussion, just some of the great work that we've already been tackling with Expanse. So Bob, take it away.
Great, thank you, Sean, and welcome everybody. So I just want to mention that there's one step between the benchmarking work that Maidar's group does and the and the Expanse early user period. And that's an extensive reliability testing where we load up the system all out for about 4 days running applications on the machines. To just make sure that everything's working, working effectively. But the Expanse, the early user period though, gives us a chance to do something else. I think of the early user period as a real win-win. So for these users who are getting onto the system, they're getting a chance to get some science done without burning their exceed allocation. And for us, we're getting additional feedback on how everything is working. So we had the 32 groups that signed up for the early user period and actually ran jobs on the machine. I'm just going to highlight a few of these. We have a convenience store chain here on the West Coast that has a tagline, "Too much good stuff." And when we get into the applications, I think that's what we're always dealing with. There's just too much good science going on. But I'm going to highlight 3 of these, one each from the life sciences, the physical sciences, and from engineering. So Sean, if you want to go to the next slide. So this is a project that I highlighted from the life sciences. This was done by a researcher at UCSD. His name was Siavash Mirarov. And he focuses on the construction of phylogenetic trees. So this is all done using genomic sequence data. And he used Expanse in 2 ways, both the CPUs and the GPUs, in order to construct 2 of the largest phylogenetic trees ever created to date. So on the left, I'm showing his work on a bird tree of life. So he constructed 2,000 different trees of more than 300 bird species, and this was based on 150,000 genomic regions. For this kind of a project, the workload was executed on Expanse's GPUs. And on the right, I'm showing a completely different unrelated project. Here's where he tried to construct a tree of life of microbial species. So this is an enormous tree. It's based on 600,000 microbial species using 380 genes. The approach is different. Here he's using a divide and conquer algorithm, and this could be distributed over many CPU nodes. And he found that Expanse just gave him great performance for both of these applications. So Sean, if we go to the next slide. Right, so this was the example I wanted to highlight from the physical sciences. This is done by David Radis. He's an astrophysicist at Penn State University. And really interesting problem where it's kind of at the intersection of the very large and the very small. So work that's done in large-scale colliders, like a Large Hadron Collider, it was looking at extreme temperatures, but low densities. And they're really interested in how hadrons, so these are particles that are made of quarks, like protons and neutrons. At these extreme conditions, they'll actually melt into a quark gluon plasma. But this can also happen in a very different regime during the merger of neutron stars. So the temperatures are much lower, or low relative to what we're achieving in the colliders. But the densities are much higher. And they believe that the same thing is happening, that these hadrons are being condensed into this quark gluon plasma during these mergers. So he's been doing numerical relativity simulations, to try to get at whether or not we could detect these QCD phase transitions in these mergers. And these also have implications for the LIGO project of, informing the scientists of what they should be looking for. So on the left-hand side, I'm showing a visualization from the simulation. 2 main regions that they want to be interested in is the surface in blue, which is showing essentially the core of the neutron star merger, where we have very high densities. And then also the regions in red, which is where we believe that the neutrons and the protons are actually disintegrating into this quark gluon plasma. David also provided us with scaling data, and he found that his AMR, adaptive mesh refinement code, was performing extremely well. He was finding scaling at large core counts. At 2,048 cores, it was better than expected. And he also said that this transition to the EPIC processors was quote unquote surprisingly painless. And Sean, next slide. And then finally, I'm going to highlight one example from engineering. That this is work done by Yi Yao at Duke University, where he was interested in doing simulations of these hybrid organic inorganic perovskites. So these materials are of tremendous interest now. They are very promising candidates for photovoltaic applications. The particular compounds that he's looking at, though, are extremely difficult to simulate. He's looking not only at a fairly complex crystal, but with defects and substitutions. So because of that, for this particular system, he needs to simulate 751 atoms, nearly 7,000 electrons. So this is really pushing the limits of DFT calculations. So he ran this on Expanse. He's been getting some great results, and he's looking forward to really diving into production. So with that, I'm going to wrap up, and thank you, Sean.
Bob, that was terrific. Thank you. So I think you can see that, you know, in a short amount of time, we've gone from getting the system in-house, and now we're at a point where, you know, we are essentially fully operational. As Mike mentioned, we concluded a very, very successful NSF review, and we await the formal go-ahead to move this into production operations on behalf of the community. We have a bunch of folks who are queued up to do that, jump on the system. So I'd like to have the other panel members please open up their video and audio. So I might toss a couple questions at folks here just to keep things going for the last few minutes that we have. Again, terrific presentations from all of you. Bob let slip there. He started to say Comet and he meant Expanse. And so I'm just going to pick up on that and toss this over to Mike and ask a question really, you know, so Expanse is a follow-on to Comet in many ways. Can you maybe comment on some of the things you learned and did with Comet, which you are also the PI of, Mike, and how that informed what we've done with Expanse? And then after you do that, so some of the others in the team might want to chime in too about lessons learned from Comet.
Sure. Well, Comet was our first large long-tail system. Although we didn't have an island design quite like Expanse, we did have the notion of full bisection bandwidth within a rack, and then just lots of racks. And we would limit job size to fit inside of one rack. Now on Comet, that was 1,700 cores. On Expanse, that's 7,100 and something cores. So one rack is quite a nice HPC system in its own right. So that's one thing. The other is that you know, we really push science gateways as the main way to access the compute, and we you know, we support 20 or so gateways on Comet, and those are moving over to Expanse as we speak. The astounding thing there is that you can support so many unique users through gateway access as compared to command line. Right now, we're up to 80,000 unique users on Comet in 5 years. And so, you know, this is truly a high throughput, high capability system. Yeah, I think that's all I would want to say about that.
Thanks, Mike. You mentioned the scalable unit. I know Christopher's, this is near and dear to his heart too. This is a large part of an idea he pushed forward as well. And one of the questions came into the chat, a couple around the expandability. You know, we can, with the current system, we can add 4 more of these units. In fact, one of the comments relates to we have plans now to actually add a rack to Expanse. So that would be under our own funding to make that available for additional collaborations with industry and so forth. So and it essentially, we've got the system was built with that in mind, and so that's something that's going to be very helpful. I also wanted to ask Maidar about on the application stack. You're using SPAC now. That's a new thing for you. How has that played out in terms of? I mean, I think you've got hundreds of applications on Comet. And is it relatively easy? Is it a heavy lift? Tell us a bit about that.
Sure. Yeah. So yeah, I think we already started testing SPAC on Comet, with trying to replicate the stack even before Expanse arrived. And one of the nice things with SPAC is that there's a pretty large development community that's already working on a lot of the standard applications. So for us, it was a natural choice to kind of go there, because one of the lessons learned from Comet is that with the long tail comes a huge software stack deployment task, because basically you get a lot of different applications with rapid changes. And going with a community approach in terms of using something that's already there helps you, cut down the amount of time you spend building and installing these applications. So we could get to close to 90% of the application stack without much change to the community setup, except for some flags that are specific to AMD and so on. And on top of that, we've seen quite a big buy-in from a lot of other AMD customers, I think, who want to do a similar thing. So AMD is also driving the application development within SPAC on their side. So we'll start getting performant SPAC-based builds from them, and the plan is that they will eventually push that up into the mainstream SPAC distro. So it's going to be useful for the wider community too, like in terms of what we test and what we come up with. Now, for the applications that were kind of unique and didn't have SPAC-based builds already, my team with Jerry, Marty, Nicole, we all kind of looked at what could be done, and we've started developing SPAC packages for them, and we'll push that back to the mainstream also once we have them all tested and running well on Expanse.
Thank you for that, Maidar. Christopher, I'm going to toss something your way. You intercepted a lot of innovations in terms of cluster management and the Lustre file system. Maybe just highlight one or two things that you learned from the Comet experience that informed the design of the system.
Sure. I mean, I think I talked about one of them, which is the issue with the small I/O, and I think that was something that was seen, kind of industry wide as far as the impacts of a small I/O on Lustre, and that certainly guided our design of the Lustre file system. We worked closely with Aon to try and address those issues, and I think that's so this is kind of how we came up with what we did, specifically using both Lustre features as well as newer hardware, taking advantage of things like NVMe, which is much lower latency, combined with things like the data on metadata. That was one of the issues we really wanted to address, and we hope that that we've done a good job, and that it'll prove out with an Expanse. The other thing you mentioned about or we all mentioned about the SSCU and kind of this island design, and that is another area where and it was really one of the things, like the aha moments in designing Expanse, where I think a bunch of us came together and understood a lot of the benefits to kind of converging about our racks. We're on a Comet, we had separate GPU racks from compute racks, and with Expanse, by moving the GPUs into the same racks as the compute, it gave us several advantages. One of them is, of course, redundancy, or at least some fault tolerance through redundancy. As Mike has said, each one of these racks is basically a decent supercomputer in itself, and that's kind of reflected in this design. If you lose one rack, you still have the same capabilities, lessened a little bit, but basically the same capabilities within each one rack. You don't lose access to all the GPU nodes or all the compute nodes. We still have access to that. And so that was another one of the big features of the SSCU, and that one of those lessons that we learned. So we do have more of a true island design in Expanse. So it's an island not just in terms of IB, but in terms of resources available.
That's terrific, and it's really about making the maximum use of the hardware you have and not isolating it. Bob, I wanted to toss something your way. There's 128 cores on a node, and what are the challenges around applications and use of threaded applications and hybrid applications? You want to talk a minute about that?
Yeah, thanks, Sean. So within my group at SDSC and also the distributed group in Exceeds, Extended Collaborative Support Services, we see a lot of challenges and a lot of opportunities with these large nodes. We haven't had access to 128 cores in a node before. Some applications that had been going to multiple nodes just in order to get enough compute power may start fitting entirely within a single node. But of course, as Mahidar talked about the architecture, the new layout, there's going to be some challenges in making sure that we're making effective use of memory, the processor features. So we're taking this very seriously. In fact, we're already working with AMD to arrange for training for our staff to make sure that we're ready to support these applications.
Thanks, Bob. That reminds me, there is an AMD user forum tomorrow at 8 o'clock Pacific time. And if you go to the sc20.sdsc.edu site, you can register for that forum, a great community evolving. There was a question that came in the Q&A also about the use of OSG and what do we see happening there? I mean, I'm not the guy there. If Frank Werthwein were here, he could comment, but I can say, just a couple things. One is, expanding beyond virtual organizations. So, LHC, for example, being perhaps a virtual organization that would use the OSG capability, but also opening that up to any general user who wants to submit a job via OSG. And that's work that Marty has been supporting, and we anticipate doing that, as well as growth in using not just the CPUs, but the GPUs. So if anybody else on the panel has any thoughts or knowledge about that, I welcome any comment on that point.
Yeah, I can chime in. I'm on the OSG Council, so I know a little bit. So I expect a continuation of the usage we've seen from LHC, CMS, LIGO, IceCube, Xenon 1 ton. But I would imagine, OSG is not only the infrastructure, they are also a virtual organization that uses their infrastructure. And through OSG VO, you see, a variety of scientific uses from, molecular biologists and other kinds of usage. And so, I think that's going to continue. I'd like to see new projects come in this way. LSST is moving toward, commissioning, and they've got a lot of, data image processing jobs that they need to do as a part of their data challenges. And so I would hope that they would also show up.
Thanks, Mike. We're about out of time here, and my team is asking if I can share one last little video with you. So thanks to all the panel members. This is terrific. Let me see here. I'm going to share one final video here that I think you'll find kind of cool and interesting. This is a time lapse of the build. You see a lot of people running around very fast. It's time lapse, and they're all wearing masks. So this is, let me see if I can successfully share this with you and say thank you to everybody for attending. And please check out that we have a Cloud Bank panel tomorrow, as well as the MD user forum that I just mentioned. So let's see if I've got the right video.
When we designed Expanse, we wanted to create a system for computing without boundaries. We wanted to erase the limits of a traditional supercomputer and more seamlessly integrate with remote instruments and data sources, public cloud providers, campuses, and other cyber infrastructure providers. The Expanse architecture, coupled with innovative software, high-performance networking, and operational policies, expands the physical confines of the machine room and redefines the supercomputer as part of an integrated ecosystem that serves all of science. Cloud integration also gives users access to new GPUs and processors as they become available from public cloud providers. This is just another example of how our approach to computing without boundaries gives the community capabilities that they just can't get with a static HPC system. It is the tool in the scientist toolbox that ties everything together. High throughput computing, cloud computing, gateway computing, edge computing, data intensive computing. Expanse is where the next generation of discoveries will happen, and there's really no limit to what's possible.
Thanks again, everybody, for joining our webinar today. And please check out our SC site, sc20.sdsc.edu, for more upcoming cool talks and information about what SDSC is up to. Just wanted to remind folks, for those of you joining there, you'll be getting information about the giveaway sent via email today if you were wondering about that.